All right, let's talk about a hidden force that honestly keeps our entire modern world from shaking itself to pieces. It's called mechanical balancing, and it's the real unsung hero that makes sure everything from your car to a massive power plant runs smoothly and, safely.
You know exactly what I'm talking about. It's that crazy violent wobble from your washing machine when it hits the spin cycle. Or maybe a ceiling fan that sounds like it's about to achieve liftoff. Well, that violent shaking, that's the exact problem we're going to get to the bottom of today. And it's not random. There's a very specific reason it happens. And lucky for us, a pretty brilliant way to fix it.
Okay, so here's our game plan. First, we'll look at why machines vibrate in the first place. Then we'll explore two fixes, the simple approach, which is static balancing, and then the more advanced solution, dynamic balancing. And we'll wrap it all up with how you actually choose the right method for the job. So, let's get right to it and identify the villain of our story. What's this invisible force causing all this chaos? Well, it all boils down to one simple concept, unbalance. At its core, the problem is actually surprisingly simple. Just picture a spinning disk that has a tiny little heavy spot that's just a bit off-center. That's it. That's unbalance. It just means the object's true center of weight, its center of mass, isn't perfectly lined up with the center of rotation. And the results of that tiny imperfection, they are huge. As that part starts spinning faster and faster, centrifugal force grabs that heavy spot and just yanks it outward over and over again. And that creates all the shaking, the noise, and some serious wear and tear on the machine. The key thing to remember is that even a teeny tiny imbalance can have a massive destructive effect at high speeds. All right, now that we know the enemy, let's talk about our first solution. This is the go-to, straightforward approach for the simpler problems. It's called static balancing. They call it single plane balancing for a reason. It corrects the unbalance in, well, a single plane. The fix is basically one-dimensional. The goal is super simple. Find the heavy spot and then counteract it. You either add a little weight on the opposite side or remove a little weight from the heavy spot itself. And that just nudges the center of mass right back where it belongs, on that axis of rotation. So when is this the right tool for the job? Well, you're looking for objects that are shaped like a disc. Think wide but not very thick. Because the part is so thin, any imbalance is really just happening in that one flat plane, which means a single correction is all you need. The key rule of thumb here is what's called the length to diameter ratio, or L/D. If the object's length is less than half of its diameter, static balancing is almost always going to be enough. And you see this method used all the time in the real world. Things like fan blades, the pulleys on an engine, or grinding wheels. These are all classic examples where the object's width is super small compared to its diameter. They are just perfect candidates for a simple static balance. Okay, so static balancing is great for thin, disc-like things. But what happens when the rotating part is long and cylindrical, like a drive shaft? Well, the problem gets a little more twisted. Exactly. With these longer parts, you can get into a weird situation where a heavy spot at one end is kind of canceled out by another heavy spot at the other end. So if it's not spinning, it might seem balanced. But the second you spin it up, those two forces create this aggressive, wobbling, twisting force. And that is a whole new kind of problem. And this new troublemaker has a name: couple unbalance. You've got two equal heavy spots, but they're on different planes, and they're pulling in opposite directions. As the part spins, these forces create a twisting motion, a couple, that makes the whole thing want to wobble from end to end. Think of a football that was thrown really, really badly. That's the kind of motion we're talking about. And the hero that can fix this problem? It's called dynamic balancing. Because that twisting action is happening on two different planes, the solution also has to be applied on two different planes. This method is the whole package. It takes care of the simple static unbalance and that much more complex couple unbalance all at once. So dynamic balancing is what you use for longer cylindrical objects. And our guideline just flips. If that length to diameter ratio is 0.5 or greater, you absolutely need this method, no question. Why? Because at that length, those twisting forces become way too significant to ignore. And it's also the go-to standard for any kind of high-speed machinery where even the tiniest wobble can be totally catastrophic. And we're talking about some seriously critical components here: the rotor spinning inside an electric motor, the long shaft in a massive water pump, and of course, the drive shaft in your car. All of these things spin incredibly fast and would literally tear themselves apart without very, very precise dynamic balancing. Okay, so we've met the two methods. Now for the really practical part. How do you actually choose between them? Let's break down the deciding factors. If you remember one single thing from all of this, make it this number, 0.5. The length to diameter ratio is really the golden rule. Is the length less than half the diameter? You can probably start with static balancing. Is it equal to or more than half? Then you are definitely in dynamic territory. It's the most reliable place to start. So let's just lay it all out, side by side. Think of this as your ultimate cheat sheet. Static balancing. One plane for disc-like shapes, and it solves that simple up and down hop or jump. Dynamic balancing, two planes for long cylindrical shapes, and it solves that nasty end-to-end wobble. See? It all comes back to the shape and that LD ratio. But here's a really cool piece of professional advice. While that LD rule is great, it's not absolute. Speed. Speed can change everything. For something like a super high-speed fan blade, even though it's a thin disc, engineers will often still use two-plane dynamic balancing. They do it just to correct for the absolute tiniest twisting errors that become a huge deal at incredibly high RPMs. And that really gets us to the key takeaway. Achieving perfect balance isn't just about finding a heavy spot. It's really a calculation that's based on the object's shape, its length, and its diameter. And, crucially, how fast it's going to be spinning. It's the combination of all three of those things that points you to the right method for a smooth, stable machine. So I'll just leave you with this thought. As you go about your day, think about all the things around you that are spinning. The hard drive in your computer, the engine in your car, the massive turbines generating your electricity. Every single one of them is relying on this invisible, precise science to keep our world humming along just about perfectly.